Hi, in this video, we'll be going through how are finitely generated modules related to free modules. And by going through what are free modules, we can talk about structure theorems later on. So let's first start with some definitions. So we let R be a ring with 1, and in this preceding section, we shall denote modules with the term left modules for easier reference. And we extend the notion of adding two submodules to the sum of finitely many submodules as the following. So the sum of n1 to ni, where n1 to ni are all submodules of M, is the finite sum of the set like this. So we denote it by this following. And we can denote a subset A of M, and we let Ra equals to the set of all finite sums of R and A together. So we call Ra a submodule of N generated by A. If N is a submodule of M and N equals to Ra, then we say that A is the set of generators or generating set for N. Or we can also say N is generated by A. And a submodule is finitely generated if this A is finite. So it's generated by some finite set. And we say a submodule is cyclic if there exists a single element such that N equals to Ra. That is, R is generated by one element. And so a submodule N of R module M may have different generating sets. For instance, the set N always generates itself. And if it's finitely generated, the only thing unique is that the number of elements in the minimal generating set is the same. But this minimal set of generators may not be unique in general. And if N is not finitely generated, then they might not have a minimal generating set in the first place. And so with that notion of sum, we can now talk about what is a direct product and direct sum. And we let M1 to Mk be a collection of R modules, and the collection of K tuples where each component lies in M1, Mi, with the addition and action of R defined component-wise, will be known as the direct product and can be denoted as M1 multiplied all the way to Mk. So it's a Cartesian product. And it is evident that the direct product is again an R module. And sometimes this is known as an external one, direct product. And this direct product can also be referred to as the direct sum when it's finite. So take note what I just said. When it's finite, then this direct product and direct sum are equivalent. And in general, they could be different, but there is a way to define a direct product and direct sum in a general sense, and we'll get to it. But first, let's talk about finite, where these two are equivalent to each other. And the proposition shows that when a module is isomorphic to a direct product of its submodules, is analogous for modules of groups being direct product of two subgroups. So let's do some proposition first, and we see that we can do a projection map from this direct product into the direct sum, and that's why we say they are similar and they're isomorphic. And then we see that the intersection between this direct sum is 0. And so this means that every x can be uniquely written in the form of a1 to an added together for some ans in the ni's. And so the proof follows just like in proving in our groups that the direct sum and direct product are equivalent. So to prove 1 implies 2, we just suppose that for some j, 2 fails to hold, and we have aj an element of this following. Then aj will equals to a1 plus all the way to ak for some ai in ni. And so this element will be a non-zero element in the kernel of pi, which is a contradiction because this is an isomorphism, so the kernel is 0. Now we assume that 2 holds, then we can see that for 2 elements in Ni, we have this to equal to each other. When they are equal, then you can just take like the aj minus bj equals to the following. And since 2 states that it must be 0, here is 0, here aj must equals to bj, and since j is, we can do this for every j, this means that x can be written uniquely. And finally, to see why 3 implies 1, we observe that the map is clearly a surjective R-module homomorphism, and so we just suffice to show that it's injective, and it will complete the proof. And 3 implies that it's injective because you write it uniquely, so the kernel must be 0. So if M is an R module with it is equals to the sum of its submodules, and it satisfies any of the condition above, then we can say that it is an internal direct sum of ni's to nk. And by the proposition, every element of M can be written uniquely as a sum, and it also states that the internal direct sum is isomorphic to the external direct sum. So in general, in a general sense, we want to see the difference between direct product and direct sum. Then we can take any R module and form the set of countable tuples, an infinite sequence of M, where Mi is an element of Mi, capital Mi. Then it's like a Cartesian product, and then we just define addition and multiplication as the following. Then the direct product will just be the Cartesian product of all these mi's. So it's like this. But the direct sum will be, you have to stop at a certain point. So it's just the end such that there's a cutoff such that everything at the back is 0. So that when you add them up, the sum makes sense. One can also define the direct sum and product in a general sense that is not even countable. And I'll leave you to read the constructions. But, so you can see now in general, the direct product and direct sum may not be the same, because the direct product is in infinite tuple, but the direct sum you must cut off somewhere, or else when you add them up, it won't be well defined. So we note that in the infinite case, the direct sum and direct product are different, and this can be even clearer with the universal properties of direct product and direct sum. So for the first one, we have a universal property for direct sum, and it states that if you have a collection of R modules indexed by some set, then for any R module n and an R module homomorphism phi of alpha from M alpha to n, then there is a unique R module homomorphism from the direct sum to n, making the following diagram commute. And this is really just taking, so basically what you're saying is every component you can project into n. Then now you take this component, you project it into the direct sum before projecting it into n. So the diagram commutes in a sense. So what you want to just do is you go from m n, you just see where it lands in this direct sum, and you just project that thing down into n by letting the rest be 0. So that's the gist of it. And we can just see that for any collection of maps, we can just define the phi to be the sum of all this. Then the summation will be well defined, and since there's only finitely many non-zero terms, we see that the diagram will commute by design. So the uniqueness is then clear also, because if you have two of these, you can do the same thing and show that it's the identity map. And it's a very standard trick. And then you can just check that this phi is indeed a R module homomorphism, which I'll leave it to you, because that is just really going through the axioms. As for direct product now, we see that there will be a unique R module homomorphism from n to the direct product. So you can see the difference now between the direct sum and the direct product is that for the direct sum, your homomorphism goes from the sum to n. But for the universal property of direct product, what happens is you go from an R module to the direct product. And so how do you read this is that you just need to define n to go to alpha. So you can imagine you have a tuple, then each one is like alpha 1, alpha 2, then you just take the phi of n at each of this coordinate, and that's how you project it into it. And then you see that the diagram will commute and the uniqueness is clear. So again, it remains for you to check that it is a R module homomorphism. And we can actually define the direct product and direct sum for arbitrary case to be using this universal property, which in higher courses they do. So the next thing to note is that an R module is said to be free if every element X there exists non-zero elements of R and unique elements of A such that X is a sum of it. So what is important to note here is the use of the word unique. So we say that in this situation, A forms a basis for F, or you can say a set of free generators, but a basis is more used. And if R is a commutative ring, then the cardinality will be called the rank of F. And so one should note that there is a difference between having a direct sum and having a property of the free module. And really the difference is the R here. So in the case of a free module, the uniqueness is on the ring elements as well. So if R equals to Z and N1 and N2 are just Z divided by 2Z, then each element of N1 plus N2, the direct sum, will be some representation of N1 plus N2 here. However, Ni can be represented as 3N1 or 5N1 because it's quotient. So each element does not have a unique representation of Ria1 plus R2A2. And thus, this is not a free Z module on the set of this basis. And you can actually just show that it's not free in any set by the similar argument over here. And so, for any set, there is a free module and it satisfies this following universal property, where A can be mapped into the inclusion of the generated set module, and then you project it down. And when your A is finite, then we see that FA can be written as a direct sum of all these generators individually, and this will be just isomorphic to Rn. And you can see how this is very similar to when we talk about free groups in group theory videos that you can watch also. So the proof of it is just to ensure that you show that it is an R module, and really it is again showing that the axiom hold, which the details will be omitted for you. So this is the gist of what our free R module is, and is really having a basis. And more examples can be seen over here, as we can identify A as a subset of FA, where F, the function now, is just, so you can think of the free module as just some set of a lot of functions. And here really tells you how you construct it out. But what we really like to note is that when A is a finite set, then this free module is just a direct sum of all the generators. And each generator, because they're isomorphic to R under this map, then it's just a direct sum isomorphic to Rn, and we'll be done. So a corollary of what I just stated is that Fi and F2 are two free modules of the same set. Then you can find a unique homomorphism between F1 and F2. And if F is a free module with basis A, any free module in that sense, then F will of course be isomorphic to the free module generated by A. So it has the same universal properties as all these free modules. And when R now is Z, so the free module is just a free abelian group. And we can see that now that a free abelian group is isomorphic to Zn, because it's just Z direct sum, which has been stated over here. So that's all for this video, where I introduced to you free modules. This will be very relevant when we talk about structure theorem in the next video. So I'll see you again. I hope you've enjoyed it. Please like, share, and subscribe. And you can leave any of your comments down below. See you.